Okay, dimension analysis. Now let's say we got a question where we got a tension T. Now tension has the same unit as a force. Is applied to a spring. The extension X is related to T by the Hooke's law. That's the Hooke's law, which is T equals to Kx. Sometimes it's also referred as F equals to Kx, where K is known as the stiffness of the spring, how much force it can absorb to cause the deformation of 1 meter. That's what the spring constant means. What is the dimension of the K? That's the first thing. Next thing is we need to verify the dimensional correctness of the formula T for the period of oscillation of mass m suspended by a spring with a stiffness K. First thing is we need to find out the dimension of the K. To find the dimension of the K, we have this formula. So we just write the formula first. Let's say T equals to Kx. We make the K the subject. K is equal, this X can go down. So K equals T over X, because X is being multiplied on this side. Now remember, X is the length. So X is the length. T is the force. And we already know what's the unit for the dimension for the force is. So I'm just going to straight away put the dimension of the force. And I'm just going to straight away put the dimension of the length. Length dimension is just an L. Dimension for the force is M, L, T, minus 2. So the dimension of the K is this L and L can cancel out. Dimension of the K is M, T, minus 2. So now we find the dimensions of the K. That was the first thing. Find the dimension of the K. So dimensions of the K, we have just found the dimension of the K. Done. Okay. Verify the dimensional correctness of the formula. So that's the second bit we will have a look, where M is the mass and K is the stiffness. We have the dimensions for the mass, we know. We will find the dimension for the K, which we have already. So we'll just put these dimensions. What will happen with this 2 pi? 2 pi is a number, constant. A constant thing does not have a dimensions. 5, 7, 15, 2.8, they are numbers with no dimensions. So moving forward, we have the formula T equals 2 pi M over K. We want to find out this formula is correct or it's incorrect. Both should have the same dimension. Now we look at this left hand side. What's the dimension for this left hand side? It's a time. So dimension for this one is just a T. Yeah. Here the 2 pi disappear. That's a square root sign still remain here. Dimension for the mass. Dimension for the mass is M because it's kilogram. So dimension is just M. Now dimension for the K. For the K, you need to go back. MT minus 2. So that will be a M and t minus 2. The m and the m, they will cancel out. And you got left with t minus 2. Now what we can do is we can bring this t minus 2 on the top. So that is 1 over t minus 2. We can bring that one on the top and we can change this minus to positive. So that's the rule of indices. So let's change that one. So that becomes a t square. But remember, there is a square root thing as well. Now this one and this one, they kind of cancel as well. When they cancel, the dimension you got on the right hand side is also t. The answer is just a t. Now if we have a look, dimension on the left hand side is same as the dimension on the right hand side. Hence this formula is dimensionally correct. So that's a correct formula. Okay, the next thing is we have a look at the application of formula in planetary motion. For example, Kepler laws. Newton shows the combination of his laws of universal gravitational, which is given by this. He said there is a force of attraction between two bodies. The force of attraction between any two bodies in the universe is equal, directly proportional to the masses of their body. And it is inversely proportional to the distance between their center. This can be any body. It can be force of attraction between a sun and earth. You can find, we know the approximate mass of the sun and we know the approximate mass of the earth. So that's the m and the m. The big M and the small m. Doesn't matter which one you use to represent which. Then R. R is the distance between the center of the earth, from the center of the earth to the center of the moon. And we have got that calculation, that distance as well. And we can just put that one and we can find that thing. G is the universal constant. The value of the G is inbuilt in your calculator. If you got the 911, you can go to the constant, shift number 7 takes you the constant. You can choose which constant and it can tell you the value. Now we can rearrange the formula. To make G the subject, and we can find the units or dimensions of the G. Okay. So when we look at this formula, it leads to the prediction that the planet should move in an elliptical orbit around the sun. Now since the gravitational force is central, it follows that a planet A moves in a plane that has a constant angular momentum. This second fact is equivalent to the Kepler's law, which states the planet sweeps out equal area in equal times. Another Kepler law relates the time t for a planet to go around the sun to the mean distance r of the planet from the sun. Okay. To attack this problem, what we need to do is, for the dimensional analysis, we need to find the dimensional formula to assign to the gravitational constant G. We start with an equation which is F equals to G mm over r square. We rearrange this formula to make G the subject. How come G become the subject? Because we need to find the dimensions of the G. The r is at the bottom, so it comes here, F r square. M and m is at the top, so it comes at the bottom, F r square divided by mm. Hence we got this formula. Once we got this formula, we will tackle this formula to find the dimension of the G. Now, we got the formula G equals FR square over MM. So, if you rewrite the formula, now we put the units, we're trying to find the dimension for the G. We know we have already calculated the dimensions for the F. Dimension for the F are M, L, T minus 2. Dimension for the R, which is a length, is a length, meter square, so length square. Dimension for that one, I'm not going to write down M and M square. I'm going to write down the dimension for that one. This is a mass, another M, because then I will just cancel straight away. And dimension for the small m, which is a mass, is another M. It make life a lot easier. Then I can just cancel the bits, and I can see what I can simplify. Once I got that bit, I can write it down as MLT. So this M is down, it has to go up, and that will become M to the power of minus 1. And then there's an L here, and there's an L here. This is an invisible 1 here. So when the base is same, we add the units. 2 plus 1 is 3. Then we got this T minus 2. So these are the units, dimensions for the G. That will be your answer.